In this segment, I'm going to talk about the transduction of light to potential. Transduction occurs in rods and cones, which we see here, rods and cones. Both rods and cones have large surface areas to hold the photoreceptor molecule. Rods accomplish this by stacking many of these double-membraned discs, a little bit like a stack of pancakes, whereas cones do it by folding the membrane back and forth, a little bit like the old computer paper that we called fan-fold paper. The light-sensitive pigment is called retinal, and retinal is an aldehyde of vitamin A. When exposed to light, this form, 11-cis retinal, is converted to the all-trans form of retinal. The bond right here is boosted to a higher energy state, and it allows the rotation of this region and then the reformation of the bond. This isomer is no longer sensitive to light in the all-trans version. Well, this animation shows you what's happening. H nu here is the abbreviation for light. We'll do that again. This is the opsin molecule. There are 7 transmembrane regions, and inside here, embedded in the opsin, we see the chromophore. This is retinal, and it's in its cis form. On the right-hand side, we're looking down at the molecule, and once again, we can see the retinal in the center. This form has a slightly purplish look to it, a rose-colored look, and in fact, the word rhodopsin comes from the Greek rhodo, which means rose. When light strikes the retinal molecule, it is converted to its all-trans. That gives a little kick to the opsin molecule. This triggers the transduction process. And this molecule appears whitish. We usually refer to it as being bleached. And in its bleached form, rhodopsin can no longer be stimulated by light. Here we're looking at the actual visual cycle. Here's opsin with the 11-cis retinal, which is now called 11-cis retinylidene, and it has a nitrogen in this position rather than an oxygen. Here we have light striking. It's now converted to the all-trans form. It then leaves the opsin molecule, and in the presence of water, is converted into retinal. The retinal is then converted into alcohol, all-trans retinol, which is then transferred into the pigment epithelium, the retinal pigment epithelium, which lines the eye wall behind the retina. The all-trans retinol is converted into an ester. The ester is then converted back into retinol, but now into the cis form. The retinol is then converted to retinal. Retinal then moves back into the rod's outer segment and then is picked up by the opsin molecule and back into its 11-cis retinylidene form. You can pause this if you want to look at it any further. Inside the rod's outer segment, we see rhodopsin attached to the membrane discs here. This is one double membrane disc. Here's the rhodopsin molecule, the retinal in its cis form. In the dark, the cation channels are open, and they're opened by high concentration of cyclic GMP. Cyclic GMP opens these cation channels, which are permeable to sodium, calcium, as well as potassium. Sodium and calcium can enter the rod's outer segment. Potassium is kicked out as the voltage rises, and we can see here membrane potential somewhere near minus 40 millivolts. So in the dark, the membrane is in its somewhat depolarized state. The influx of sodium and the efflux of potassium must be balanced by the sodium-potassium ATPase pump. Otherwise, this membrane would completely discharge and the voltage would be at zero. So this pump is working overtime in the dark, trying to keep the potassium in, the sodium out, and maintain the membrane potential at least at minus 40 millivolts. Now, light strikes the rhodopsin molecule. We're now converted into the all-trans form. It stimulates the G protein with the GTP attached. The G protein, called transducin, then stimulates cyclic GMP phosphodiesterase. The phosphodiesterase then breaks cyclic GMP down into 5' GMP, and as the cyclic GMP concentration diminishes, cyclic GMP leaves the cGMP gated cation channels and they close. These channels close, causing the voltage inside to drop. Sodium no longer comes in, but potassium is still able to go out. So as the positive charge leaves the cell becomes more negative, and we see now somewhere down around minus 80 millivolts. To avoid continued stimulation, the photoreceptors become inhibited. We call this light adaptation. Once again, here we see the 11-cis retinal. It is now triggered, and at this point, the light-activated opsin, with the retinal now missing, is phosphorylated by an enzyme called rhodopsin kinase. Rhodopsin kinase operates under low calcium conditions. In high concentrations of calcium, rhodopsin kinase is inhibited by another protein called recoverin. The calcium recoverin complex inhibits rhodopsin kinase. As calcium levels drop when exposed to light, recoverin then disinhibits rhodopsin kinase, and we see the phosphorylation. Phosphorylation continues, and at this point, another protein called arrestin moves up, binds, and totally inhibits the inactivated molecule. In addition, in low calcium situations, guanylate cyclase activity is increased. Therefore, in the light, we are creating cyclic GMP to open the sodium and calcium channels. This seems like an apparent paradox. Since cyclic GMP opens sodium channels in the dark, why would we want guanylate cyclase activity to decrease in the dark and increase in the light? In light, the activated guanylate cyclase would counter the effect of the cyclic GMP phosphodiesterase. This also helps to prepare the cell by starting to accumulate cyclic GMP for the recovery process, so that when we go back into the dark, cyclic GMP concentrations are high enough to open up these cation channels. In addition, if we allowed this activity to continue in the dark, we may actually have an overproduction of cyclic GMP. Too many sodium channels would open, and this could depolarize the membrane even more. We can think about this as a balance between cyclic GMP production and cyclic GMP degradation by the phosphodiesterase. In this figure, we're looking at the guanylate cyclase. These are the membrane-bound regions. Calcium binds to a protein called guanylate cyclase activating protein, and this inhibits guanylate cyclase. So the active site right here is inhibited when calcium levels are high. When calcium levels go down, the active site now is able to pick up GTP and then convert it into cyclic GMP and inorganic phosphate. So here I'm going to be showing the production and then eventual degradation of cyclic GMP. We start with GTP. In the presence of guanylate cyclase, two of the phosphates are cleaved at this point right here. The third phosphate is then swung around and connected, forming this cyclical region. So this is cyclic GMP. In the presence of the phosphodiesterase, cGMP phosphodiesterase, and water, this bond is then broken, and we now have 5' GMP. Another process of adaptation is called translocation. In the dark, here we're looking again at the rod's outer segment, we see lots of transducin molecules. Transducin is the G protein. We see a few arrestin molecules and a few recoverin molecules. And in the inner segment, we see a lot of arrestin molecules and some recoverin molecules. When exposed to light, however, the arrestin molecules are moved up into the outer segment, and transducin is moved down into the inner segment. Recoverin is also moved down into the inner segment. So by reducing the number of transducin molecules and increasing the number of the inhibitory arrestin molecules, we now are inhibiting activity in the presence of light. This figure is from the work of Kong et al. In 2006. It's a simulation of that figure. To see the original figure, you'll need to go to the works of Kong et al. In photoreceptors adapted to light, the outer segment contains little or no transducin. All of the transducin is in the rod's inner segment. However, arrestin, the inhibitory protein, is located primarily now in the outer segment and not so much in the inner segment. In dark-adapted photoreceptors, The outer segment now is primarily composed of transducin, and the inner segment, we see the arrestin starting to accumulate and very little transducin. This image is showing us the open sodium channels. This is now in the dark. These are cyclic GMP gated channels. They're open. Sodium and calcium can move in. As the positive charge builds up, potassium begins to move out, sodium back in, potassium out, and we have a dark current occurring here. The activity of the ATPase here, pumping sodium out and potassium in, is running at a very high rate in order to keep the membrane potential from completely depolarizing. In addition, as calcium is entering the cell, since calcium is toxic to cells, we want to move it back out again in exchange for sodium. That sodium, along with the sodium coming in, is then pumped back out again. Well, I leave this for you to read. This is a look at the amplification of phototransduction. This ends the discussion of light transduction